Every design standard reflects the world it was written for. The 1997 rules were safe, for a simpler time. They used sound engineering theory for basic loads. But the modern warehouse has changed. Complexity, perforation, interaction, and suddenly, a mathematically correct answer is not always a reliable one.
All right, let's talk about industrial shelving. Today, we're zeroing in on a really critical standard, ANSI MH28.1. This is basically the rule book for designing these massive structures safely. But we're going to go deeper than just the rules. We're going to dig into why physical testing, actually putting the steel through its paces, is the absolute bedrock of safety here, not just fancy math.
I mean, look at this. This is not the shelf you have in your garage, right? These are enormous, complex, engineered systems. And when you're dealing with something on this scale, the stakes are just incredibly high. A failure isn't just a mess, it can be catastrophic. We're talking lost inventory, damaged equipment, and most importantly, it's a serious life safety issue. That's why understanding what really holds them together is so vital.
Okay, so here's what we're going to cover. First, we'll dive into the unique challenge that bin shelving presents. Then, we'll get into why physical testing is really the only way to get a true answer. We'll also look at how the standard has changed over time, figure out where it fits in the whole MH28 family of standards, and wrap up with who's in charge and what you really need to take away from all this.
All right, first up, the challenge. You look at it and you think, it's just some posts and some shelves. How hard can it be? But the reality is way, way more complex. You've got these proprietary connections, the special properties of cold-formed steel. It's a whole different ballgame.
So, what exactly are we talking about here? Well, the standard itself defines bin shelving like this. It's hand-loaded, that's a key detail. It's made from cold-formed steel components, and critically, it uses these specially engineered clips or bolts to connect the shelves to posts that are full of perforations.
And right there, that's the core of the problem. Because of those unique clips and all those little holes in the posts, you can't just plug numbers into a simple formula and get a reliable answer for how much weight it can hold. The way all those parts interact, it creates a system that pure math just can't predict on its own.
And this little guy is a huge piece of the puzzle, the connection clip. These are often proprietary designs, meaning each manufacturer has their own unique system. So that spot where the shelf, the clip, and the post all meet, it's a super complex interface, and you just have to see how it behaves in the real world.
So if math alone isn't enough, what is? Well, that brings us to the solution: physical testing. The whole MH28.1 standard is built on this idea. Testing is what bridges that gap between engineering theory on paper and how these things actually perform under pressure in reality.
So testing really does three key things for us. First, it's how we find out a shelf's actual load capacity. Second, it lets us analyze the individual pieces, like those perforated posts, to see how they handle the load on their own. And third, it validates the whole shebang, making sure the shelf, post, and clips all play nicely together and work as a safe, integrated system.
And you don't have to take my word for it. This quote from the standard's own commentary just nails it. It says to figure out the strength of a post, you typically have to do a stub column test. That's a physical test. Why? Because all those holes make a simple calculation unreliable. You gotta test it to know for sure. And here's kind of what that looks like behind the scenes. This is a schematic from an older version of the standard, but it shows the basic idea. You can see they've got a setup to apply a specific load, and they measure exactly how much the shelf deflects or bends. This is how you get real data, not just theories.
Now, these standards don't just sit on a shelf gathering dust. Nope, they have to evolve. And the story of how MH28.1 has changed is really the story of how the modern warehouse has changed. Just look at the jump here. Back in '97, the standard was mostly concerned with basic gravity loads. How much stuff can you pile on it before it breaks? But fast forward to today, and the 2024 version is packed with super rigorous methods for dealing with seismic loading and integrating with other complex systems. The whole scope has just exploded.
So why the huge shift? Well, think about it. Shelving has completely transformed. We've gone from simple standalone racks to these absolutely massive multi-level pick modules with elevated walkways, and even systems that are tied directly into automated robots. The structures got more complex, so the rules had to get a lot smarter. Man, just to show you how serious this gets, here's a little peek at the modern seismic rules. You can see it gets super specific depending on the seismic design category of your location, which is just a fancy way of saying how likely you are to get an earthquake.
The standard tells you exactly how high you can build, the ratio of height to depth, and whether or not you absolutely must anchor it to the floor.
Okay, this next part is super important. MH28.1 is not some kind of one-size-fits-all rulebook. It's actually part of a whole family of standards, and knowing which one applies to what is absolutely key to getting safety right.
So, take a look here. On the left, we've got the industrial bin shelving we've been talking about, the stuff covered by MH28.1. On the right, that's industrial boltless shelving. Now, to you and me, they might look pretty similar at first glance, but from an engineering standpoint, they are totally different beasts.
Let's break it down. MH28.1 for bin shelving is all about those clips or bolts and has a heavy focus on seismic performance. But then you have MH28.2 for boltless shelving. That stuff uses rivets or tabs, and because those joints behave differently, they're what engineers call semi-rigid. It requires its own special kind of testing to see how it handles stress. And then you've got this other one, MH28.4. This is for the shelving you'd find at a retail store, the stuff designed for consumers. It only applies to shorter, single-level units. Its testing has nothing to do with earthquakes. It's all about consumer safety, like making sure it doesn't tip over on someone. And here's the bottom line. These standards are not interchangeable. You can't mix and match. Using the wrong one is a recipe for disaster.
All right, last section. Let's pull back the curtain and see who actually writes these rules and, maybe more importantly, who makes sure people follow them. Understanding the governance is a big piece of this puzzle.
So there are two main players in this game. The standard is developed by the Storage Manufacturers Association, or SMA for short, and then it's officially approved by the American National Standards Institute, which you probably know as ANSI.
So here's how it works. The SMA, which is made up of the companies who actually make this stuff, they get together and develop the standard. Then ANSI gives it the official stamp of approval. But, and this is the kicker, the standard is completely voluntary. Neither ANSI nor the SMA goes around enforcing it. That job falls to your local building official, the person they call the authority having jurisdiction.
Which all brings us to the big takeaway here. When you are looking at industrial shelving, when you're comparing products, you cannot just look at the capacity number on a spec sheet and call it a day. It's just not enough.
So the next time you're looking at a spec sheet and you see that capacity number, ask yourself, what's the real story behind that number? Was it validated through the tough, real-world physical testing required by the right standard? Because knowing that story, well, that's the true key to safety and reliability.